So we have been discussing the integrals of complex variable functions along different paths in the z plane. Today's session will be in continuation with our previous session, and today we will be discussing the integrals or line integrals along closed curves. Okay, the way we distinguish between line integrals along closed curves and in general any line integral is that if we are integrating along a closed curve C, then we encircle the integral's center. So this means the path of integration is a closed curve, or in other words, let us say if we start at this point, if we start the integration process, then eventually we will come back to that. Okay, and the convention is we trace the curve anti-clockwise. All right. So there is a theorem and a formula named after the mathematician Cauchy. All right. So in this lecture we will cover both of them, the Cauchy's integral theorem, abbreviated as CIT, Cauchy's integral theorem, and the Cauchy's integral formula. Okay. So we will first see the Cauchy's integral theorem, what it says, and then we will go to the connection between path independence and what we call path deformation. Okay. Now deformation is actually a term in mechanics or statics, and deformation there means change in shape or size. Okay, so here we actually change the path, but still we get the same answer, and that is what we call actually path independence. Okay, and then we will apply the path independence to closed paths. Okay, the main topic of discussion today, integrals along closed curves, and we'll see how the Cauchy's integral theorem can be applied to the result that, to get the result that for analytic functions, provided the curve C satisfies certain conditions, the value of the integral is independent of the path. Okay, and then of course we will solve a couple of examples. This will constitute the first part of the session. In the second part of the session we are going to derive the Cauchy's integral formula. Okay, and then we will see a more useful version of the same formula, or I would say a general case. And to prove the general case you require the Leibniz rule and partial differentiation, so we're not going to do that right now. That is the derivatives of the analytic functions, okay, by actually computing line integrals, and then at the end we will go to the examples based on the Cauchy's integral formula. Okay, and of course whenever we are solving examples on the Cauchy's integral formula, we may occasionally be required to use the theorem. Okay, so with that introduction, let us start the lecture. Okay, so let us now see, or let's begin by stating the Cauchy's integral theorem. Okay, Cauchy's integral theorem. Okay, as the name suggests, it has something to do with the integrals of complex variable functions. Okay, now for this theorem we are going to recall two terms that we have seen earlier. Term number one, a simple closed path. Okay, so this is a closed path which neither touches nor intersects itself. Okay, so usually all the paths that we will encounter in our problems, they will be simple closed paths. Okay, and then simply connected domain D, which is a set of points. Okay, simply connected domain means every simple closed path in D encloses only points of D and not any points which lie outside D. Okay, so if we have a simply connected domain, then the theorem is applicable. Okay, CIT. The statement is, if the function f is analytic in a simply connected domain D, then for every simple closed path C in D, the line integral of the function f with respect to z taken along the curve C is 0. Okay, so because it is an integral along a closed curve, let's encircle the center of the integral. Okay, so the Cauchy's integral theorem says that if we have a function which is analytic, okay, throughout the simply connected domain D, and you consider any simple closed path in D, its value will be equal to 0. Okay, and I would like to highlight that this is a closed curve. Okay, so if you are saying that I have a path like this and I'm going to apply the Cauchy's integral theorem, you cannot apply. The reason why you cannot apply the Cauchy's integral theorem for this path is because this is not a closed path. Okay, fine. I mean, you may apply it like this. Okay, let's say you use the path C1 from A to B, and then for some reason you come back to A by following a different path C2. Okay, then the union of C1 and C2 is a closed path, and you can apply the Cauchy's integral theorem there. Okay, C1 union C2, but only C1 is not a closed path, only C2 is also not a closed path. Okay, fine. So let us now solve a simple example based on this. Okay, we are going to find the value of the integrand, where the integrand is 1 upon z squared minus 5z plus 6, and the curve C is a closed curve, and that is in fact the unit circle centered at origin. Okay, we note that the integrand is a rational function whose numerator is a constant function and whose denominator is a quadratic function in z squared minus 5z plus 6. So we have seen that rational functions are analytic everywhere except at those points where the denominator is 0. So if the function is f1 upon f2, then f2 is equal to 0. Okay, if the function is f1 by f2. So what we will now do is we will try to find out the points, okay, which we call singularities, because at these points the function is not defined, or sometimes they are also called as poles. Okay, and they are not difficult to find. You have to just solve the quadratic equation. The poles will be 2 and 3. Okay, and now our next job is to determine the relative positions of these points or poles with respect to the circle C or the curve C. Okay, and it's not very difficult to see that both the roots of our equation are real. Okay, and if this is the closed curve C, the unit circle, then z1, which is 2, it lies outside, and so does z2, which is 3. Now if both the poles lie outside the curve C, then we can apply the Cauchy's integral theorem, because we can say that the domain D is now the set of points belonging to the interior of the curve C as well as the curve C. Okay, so if this is our domain D, then the Cauchy's integral theorem applies, and therefore the integral is equal to 0. Okay, remember, we have carefully obtained the points at which the function is not defined, which then become the singularities of the function, and both of them were lying outside the curve, okay, outside the closed curve, and therefore we could apply the Cauchy's integral theorem. Okay, meaning if we consider a different curve, let us say mod of z equal to 5/2, then you cannot apply the Cauchy's integral theorem, because for 5/2 you will have a circle like this. Okay, so one pole lies outside and the other pole lies inside, so we're going to use the Cauchy's integral formula for solving such problems. Okay, but as far as this problem is concerned, the value of the integral is 0. Okay, now we are going to see something what we call as path deformation. Okay, and of course the path independence. So the theorem on path independence is telling us that suppose we have a function f of z, okay, which is analytic in a simply connected domain D. Then the integral of f of z is independent of path in D. Okay, so here in the path independence theorem, the curve C need not be closed. Okay, look at the curves C1 and C2. Okay, both C1 and C2 begin at P and end at Q. Yes. Okay, now we can consider a curve, a closed curve. Okay, closed curve C, and let's call the curve this way. Okay, let me consider a point R here, or okay, hold on. Yeah, let's consider a point R1 here, and let's consider a point R2 here. Okay, so I can call a closed curve as P R1Q, then Q R2 P. Okay, so this is a closed curve, and because the function is analytic and we have a simply connected domain, we can directly say that the integral of the analytic function f of z along C is 0. Okay, so by Cauchy's integral theorem. Okay, now to get the result of the path independence, what we are going to do is we are going to start from P to Q. Okay, and then if we want to come back from Q to P, we are actually using a different orientation than the we are using a different orientation, meaning we are using the opposite sense of traversal. Yes. Okay, so if from P to Q it is C1, we may now assign a negative sign by the sense reversal property. Which is 0, isn't it? And once you shift any one of these two integrals to the other side, you will get back the result. Okay, so if you have an analytic function in a simply connected domain D, it doesn't matter how you change the shape of the curve, okay, or how you deform. For example, here if you imagine this curve C1 to be made up of some elastic material, you can actually pull it up and get it in the shape of C2. Okay, but still, although you are changing the path, because it is a simply connected domain and the function is analytic, the value of the integral is not going to change. Okay, so this is what we mean by path deformation. Of course, the function should be analytic throughout, only then the path independence will be satisfied. Okay, so this is what we mean by deforming a path, which is as good as changing it from one to the other, keeping the endpoints the same. All right. Now we actually talked about path deformation applied to paths which were not necessarily closed. Okay, these were starting at a different point and terminating at a different point. Okay. However, now the question is it possible to apply the path deformation or path independence thing or theorem to closed paths? Yes, it turns out that you can still apply them to closed paths. Okay, so we will see how we can apply the path deformation to closed paths. Okay, and for this we are going to consider two closed curves, C1 and C2. Okay, C1 is the outer curve that you can see in the figure 1 and C2 is the inner curve. Okay, and to apply the path deformation to closed paths, okay, what we are going to do is we are going to consider 2 points, one on the path C1, okay, any point on the first curve, and we are going to consider point B on C2. Okay, and then we are going to slit the region. Okay, now what do we mean by slitting? We are going to slit the region by introducing two curves which represent two coincident segments. Okay, so look at the second figure now. In the second figure, what we have done is from A we have drawn a segment to B. Okay, and we are calling this particular curve to be C prime. Okay, and note that this is an oriented curve. Okay, it has a sense of traversal, okay, from A to B, and then again we are going to define another curve from B to A. And this will then become negative of C prime due to the change in the direction. Okay, endpoints are the same. Okay, and if we come back to the figure 1, if we consider the curve from B to A, it is in the red color. Okay, and from B to A, sorry, just a second. Yeah, in the figure 1, if we consider the curve C prime, that is from A to B, okay, it is in the blue color, and if we consider the curve in the figure 1 from B to A, it is in the red color. Okay, now note that these are coincident curves. Okay, meaning although in these two figures you will find a tiny gap between these two curves, which I'll highlight in the pink color. Okay, in reality there is no such gap. Okay, both the curves are coincident. So what we are actually achieving here is that we have now got a single curve, okay, a single closed curve, okay, which we will call C. Okay, and this is how we obtain it. Okay, we start from A. Okay, or let me use a different color. Let me use, hold on. Okay, let me use this color. Let us start from A. Okay, I will go to A again, but this time I'll take a turn and go to B. Okay, I'll traverse C2 in the opposite sense. Again I'll go to B, and then I'll go along minus C dash from B to A. So thereby I'll complete a closed curve. Okay, so we write it in this way: C is equal to C1 plus C prime plus minus C2. Note the change in sign because we are traversing it in the opposite way. Okay, minus C2, and then again minus C prime because again we are coming back to A. Okay, now because this is a piecewise smooth curve and closed curve C, we can apply the Cauchy's integral theorem, which means the line integral along our closed curve C is equal to of f of z is equal to 0. Okay, yes. Now the thing is, this actually implies that the line integral of our function along C1 will be equal to the line integral along the curve C2 of the same function. Okay, because if this whole integral is 0 with respect to z, then we can write down the following equation. Okay, integral along C1 plus integral along C prime plus integral along minus C2 plus integral along minus C prime. Okay, now due to the sense reversal property, these two integrals automatically get cancelled, and this integral will then acquire a negative sign. And then when you shift this to the other side, you get the relation. Okay, integral of f of z with respect to z along C1 is equal to integral of f of z with respect to z along C2. Okay, see, now this particular result is telling us that what we are interested only in is in the deformation of C1 to C2. Okay, now we cannot actually, we cannot really deform it, because for C1 there has to be a point from which we begin our integration process, and then you have to reach again the same point. Okay, so if we are actually deforming it and fitting it on C2, this point also gets, I would say, displaced. Okay, and this possibility did not arise for paths which were not closed. Okay, because we had definite endpoints there. So now we have slitted the region, and by slitting we have proved this property. So we can now say that if it is a closed curve, okay, we can actually deform it into any other closed curve and still get the same value of the line integral, okay, along C1 or along C2, provided the function f of z is analytic on C1 and on C2 and everywhere in the interior of the curves, okay, or the region which lies between or which is surrounded by C1 and C2. Okay, now the function f of z may not be or need not be analytic inside C2. Okay, it may still have some points where it is not defined, but as far as the deforming of C1 is concerned to C2, the result is totally applicable. Okay. Let's now go to question 2, wherein we will evaluate this integral, and we have already considered a special case of this in our previous lecture, where the integrand was 1 upon z and C was unit circle. Okay, so this time we are evaluating the line integral of z minus a to the power n, where C is the closed curve, which is the path of integration, and here n is any integer. Okay, now, well, as I said, C is going to be any piecewise smooth and simple closed curve, and the number A is any complex number inside the curve C. Okay, now what we are going to do is we are first going to deform C to C prime. Okay, and we can do that because we have proved it earlier. So this C can be any piecewise smooth simply closed curve. When you deform C to C prime, we deliberately take C prime to be a circle which is centered at A. Okay, this complex number. Now by doing this, we are actually simplifying our integration process, because we can now use the parametric equations of the circle. Mod of z minus a equal to, well, you can take a circle of arbitrary radius now, but you have to fix the center to the point A. Okay, all right. So once we do that, then introduce new coordinates, so to speak. Okay, so let z minus a be r times e to the power I phi, which you can see here. So the same circle has been now shown in a slightly larger version. Okay, I will ignore the axis now. So the circle is centered at A. Yes, and for all points on the curve C prime, okay, they are equidistant from A. The distance between those points and A is r, and depending on the magnitude of the angle, we will go on getting different points. Okay, so if z is a plus r times e to the power I phi, what will dz be? Dz will be r I e to the power I phi times d phi. Yes, very much like the integration by substitution. Okay, so the integral then gets converted to this definite integral. Limits are on phi 0 to 2 pi. Okay, now what is z minus a raised to n? Okay, which is the integrand here. Because we have substituted z minus a as r times e to the power I phi, z minus a raised to n will be r to the power n into e to the power I phi raised to n. Yes, so this takes care of the integrand. But we also have to find the replacement for dz. Okay, and we know that now it is r times e to the power I phi times d phi. Okay, now everything that does not contain phi can be taken outside. There are two such terms, r to the power n and r, so bring them outside. R to the power n plus 1, and I is also now something which will come outside the integral. Okay, so now the integrand is e to the power I n plus 1 phi d phi, as phi goes from 0 to 2 pi. Okay, now we have to consider two different cases. Okay, case 1, let's consider a case where n is equal to -1. If n is equal to -1, then this integrand will be equal to 1. Yes, okay, and this will also be then equal to 1, r to the power 0. Okay, and integral of 1 with respect to phi is phi. Put the limits, you will get 2 pi r. Okay, now note that in our previous question, not in the previous question, the one that we solved in our previous class, integral of 1 upon z with respect to z, where c was the unit circle, we had got the same answer there. Okay, now we have found out a more general version of that. All right, yes, and still the answer is 2 pi I, meaning if you take any closed curve C, and if you evaluate 1 upon z minus a dz, then that will turn out to be 2 pi I, provided the curve C is any piecewise smooth closed curve. Okay, and a is any complex number inside C. Okay, all right, and in this case that complex number was 0, which also is the center of the unit circle. Okay, let's go to the second case now, where n is not equal to -1. Okay, so this time what we can do is we have to keep r to the power n plus 1 as it is, I as it is, and apply the formula for, for the exponential function, okay, the integral formula. However, this time if we substitute, because n is an integer, if we substitute phi as 2 pi and phi as 0 here, both will produce the answer 0, right? Because any integral multiple of 2 pi, okay, has cos 1 and sin 0, so both 2 pi and 0 will produce well, 1, right? Yeah, 1 minus 1, and then 1 minus 1 will be equal to 0. Okay, so if n is not equal to -1, the integral's value becomes 0, and if the value of n is -1, only in that case the functions or the integral's value is not equal to 0, but it is equal to 2 times pi times I. Okay, well, let's now show that this is indeed 1. That's my mistake. By mistake I took it as 0, right? E to the power I0 is cos 0 plus I into sin 0, which is 1 plus 0i. And if you now make a change and write it as e to the power I 2 pi, this is also going to be 1. Yes. So if you are raising the powers to n plus 1, where n is any integer, you are still going to get 1. Okay, same applies to e to the power I 2 pi. Okay, so that completes the problem. See, now in this problem we have actually made use of the path deformation. Okay, so what we did was we had any arbitrary closed path which was piecewise smooth, simply closed curve, and we had a complex number inside C, and we took the help of, or we used this complex number A to define our integrand. Okay, so this is a kind of a special integral. All right, then using the deformation, what we said is, okay, if we have a curve C, let us, if it is not a circle centered at A, deform our curve C to such a curve, okay, such a circular curve, call it C prime, and we now know that our integral along C and along C prime is going to be the same. Okay, yes, and we eventually had to consider two different cases: n not equal to -1, integral 0, n equal to -1, integral 2 pi I. Okay, all right. So this is all about Cauchy's integral